Okay. So welcome, everyone. I promised you that in this course we will discuss IR and UV physics of gravity. So today we're going to finish the IR part, and tomorrow will be all about ultraviolet. The question that I raised in the very beginning about the infrared physics was, what are all the symmetries of nature? That's a challenging question. But in the course of the last couple of lectures, we made some progress in understanding the first few of them. And we did so by exploiting relationships between a priori distinct areas of gravity in the infrared. We started out by defining the canvas on which we were going to paint quantum gravity in asymptotic flat space, which is to say, define what we mean by asymptotic flat space. And we then ask, well, what are all the symmetries that preserve this asymptotic structure? Now, you may have gotten the feeling that this is kind of a tricky thing. We have to find these diffeomorphism vector fields and then check that they do the things that we want them to do. And in general, this is a hard question, in particular if you want to find all of the symmetries of Einstein gravity. We then saw that there's a relationship between asymptotic symmetries and something actually observable, so or in principle observable, which goes under the name of memory effects. And we discussed how to sort of make these kind of abstract sounding symmetries more tangible in terms of some distortion of some permanent displacement of the relative position of detectors that measure, for example, gravitational wave from the merger of black holes. And then in the last lecture, we discussed another relation, which is to something quantum field theorists study, which is factorization properties of the S matrix in the low energy limit. So this was the topic of soft theorems. And I outlined to you how soft theorems are connected to the conservation laws that are implied by these asymptotic symmetries, so the conservation laws of the charges. And I also mentioned to you that some corners of these sort of infrared triangle were known, and then other corners were inferred by thinking that there should be a relation between them. So for example, the leading soft graviton theorem, the leading soft photon theorem, they were known. The leading memory effect was known, and this made sort of the BMS supertranslations more robust. The subleading soft theorem was searched for by thinking that we should not only enhance translations to supertranslations, but also the Lorentz group to superrotations. And then a subleading soft graviton and a sub-subleading soft graviton theorem were found here. And then starting from there, a subleading memory effect was found here. And then this is something some structure that applies both to gravity and gauge theory. And so people looked for other kinds of infrared relations and other kinds of corners of these infrared relations in both gravity and gauge theory. Now we said that soft theorems is a low energy expansion. So the first term in this expansion was 1 of energy, so we Taylor expand. The next term was order 1. Then the next term is then order omega, omega squared, and so on. And you might now wonder whether there is actually an infinite tower of such infrared relations going on here, which goes to the question of, is there an infinite tower of symmetries? And to highlight sort of the crazy amount of infinity here, from the leading soft graviton theorem, we got supertranslations, which is already an infinite enhancement. The subleading soft graviton theorem is an infinite enhancement of the Lorentz group. That would be a lot of infinite enhancements, okay? And so this is the question that I want to end with today on this topic. But to do so, let me maybe go back to what we discussed yesterday to make it very clear so that we're all on the same page. So here's my cheat blackboard. So yesterday, we've talked about how to map the soft theorems to celestial amplitudes, so factorization properties of celestial amplitudes. So we started in the momentum basis. here, and then we said, well, actually symmetries are made much more manifest when we go to this boost basis, which is done by doing this Mellin transform, where we integrate over the energy and trade energy for the boost weight or the conformal dimension. And so this is what we did. We had the leadings of photon theorem, the leadings of graviton theorem, and the subleadings of graviton theorem worked out in the energy basis. We then applied the Mellin transform to recast them as celestial amplitudes, which I told you yesterday or the day before, look like correlation functions in a two-dimensional conformal field theory. So those are the Mellin transformed soft theorems. So what we said was that you have an n-point amplitude, so these are the n particles. Then we stick in one soft particle, in this case a soft photon. When you Mellin transform, all these operators have a definite conformal dimension or boost weight delta and spin j under the two-dimensional global conformal group. So specifically for the soft photon, the operator that we stick in here will have spin 1, 2D spin 1. And then we saw that the 1 over omega pole on the right-hand side after we Mellin transform becomes a pole in delta, and delta equals to 1. So I move that pole over, multiply the left-hand side and the right-hand side by delta minus 1. That makes the right-hand side finite. And here I have now a limit, delta goes to 1. And what I will do is I will define this to be my special soft operator. So this is the operator that I stick in to my n, that I add to my n-point amplitude of all the other hard particles. And then on the right-hand side, I just have the n-point amplitude, which takes now the form of an n-point correlation function in a 2D theory. So these are these operators that we insert on the celestial sphere, and which have definite boost weight delta and spin j. And we saw that this takes a very simple form on the right-hand side. It looks like the correlation function for a current. So that motivated the definition of this soft operator. Let me write this out again here. So staring at this celestial amplitude in this conformally soft limit motivated the definition that this guy here, which is my soft operator of dimension 1 and spin 1. So I can call this a current because this is really the correlation function for a current. Okay? So now, what does this current do? Well, this current is a conserved current, so you can see that if I hit the right-hand side by del Z bar, let me abbreviate this by, so this motivated that this current is actually holomorphic, that's conserved. And as you learn in quantum field theory, you can construct Noether currents from such conserved operators. So the Noether current here that we would obtain is something that comes with a symmetry parameter and this operator. And in order for this Noether current to be conserved, since J is already conserved, it also means that this parameter has to be conserved. And this is something that you learn in two-dimensional conformal field theory. If you have U1 currents, there is a symmetry associated to it. This current is holomorphic. You can construct a Noether current that is conserved. And then from that Noether current, if you integrate that current, you can obtain a charge. And that's the charge associated to this symmetry. And you can see here from this correlation function, if you hit the right-hand side by del bar, it becomes 0 up to the points where the other operators here are inserted. So these will be Dirac deltas in those other locations. And this is nothing but the water density, right? So we have established that the soft photon theorem, once recast in the boost basis, takes the form of a correlation function for a current, from which you can then, by taking a derivative and looking at the conservation of this current, write down a water density. So, and this soft photon theorem, as I explained the day before yesterday, I think, has to do with some large gauge symmetry, which I call super phase rotations, because for matter fields, the way they act is they give a phase, but the phase is not a global one, but a local one. And so this superphase rotation symmetry has this water density when we cast on the celestial sphere. So let's look at the graviton. This was maybe a bit fast yesterday, which is why I'm gonna write this down slowly today. So there too, we had the soft graviton theorem. We cast it in this boost basis. This is the correlation function that you get. I will do the same here. I will call this my soft operator, because that is what it is. Now it's spin 2, let's say plus 2. Let me call this O soft. But we also discussed that this doesn't look like something that you recognize from a 2D CFT. So what do we do? To make it look like something that we recognize as a water density for a conserved operator. Yeah, we take a derivative. Okay, so let's do that. So then I have del bar of this operator. And, well, del bar on this kills what's in the numerator. And then this looks very much like the upstairs one. So let me give this a name. Let me call this P. And then what you can see, once you have taken already one derivative, it looks like the above one. So in order to get the conservation equation for the current, what do we do? Well, we take another derivative. And so then this looks like the above conservation law. But I want to emphasize here that taking derivatives, so these operators here that we put in there, the ones that I circulated, and all the other guys are primaries. We established yesterday that when taking plane waves to the boost basis, they take the form of conformal primary wave functions, and we constructed operators associated to these wave functions. So these operators on the celestial sphere are primaries. Do you all know what that is? Okay. Oh, so the subscript J was the spin, the 2D spin. That was, so the curly one was the Noether current. So to construct the Noether current, you take your conserved operator and you convolute it with some symmetry parameter, and then you integrate that and you get the charge. And you get global charges when the symmetry parameters take, so in this case, when the symmetry parameter is constant. Then that J was already the Noether current. Okay, so we discussed yesterday for scalars, we explicitly wrote down a transformation law under bulk Lorentz transformations and boundary global conformal transformations or Möbius transformations. And we saw how the scalar wave function should transform to be called a conformal primary in a 2D CFD. Okay? If you don't know what these things mean, you should ask, or we can also do it in the Q&A session. I can review some of the basic 2D CFD stuff in case this is not known. And by the way, I will not be here in tomorrow's Q&A, so if you have questions, you should ask today. Okay, so if something is not clear, please ask. If you don't ask, I assume you know, and then I'll go on, okay? So, okay, we have this correlation function. We take one derivative, but taking derivatives takes a conformal primary to what? A descendant. It's not a primary. It can happen that you take derivatives and you go from a primary to a primary. And this is actually what you do in CFD in order to find symmetries. So if you find all the primary descendants, you find the symmetries. And I'll come back to that point in a little while. But bottom line here is that this was the primary operator. I take a derivative, so P is a descendant. It looks like a current. It has the same correlation function as this guy once I've taken this derivative, but it's a descendant. This is the guy that is the primary. And so if I look at the conservation law, the conservation equation for this primary, it's taking two derivatives of this O soft delta equals 1 and spin 2, that is 0. And this is something that you don't normally see in 2D CFD, right? We know the current is holomorphic, it gets hit by this and it's 0. We'll do the stress tensor in a moment, but stress tensor in 2D CFD also satisfies an equation like this. This is not something we normally have. And this is a novelty in the celestial conformal field theory. the difference between between operators that satisfy this conservation equation, and as well as the stress tensor, which I will get to in a moment, is that there are more symmetry generators which do not satisfy the unitarity bound in CFT. So this 2D celestial conformal field theory, from the point of view of 2D, is not unitary, but from the point of 4D, it's completely fine, it's unitary. We have 4D unitarity. It's just that when we recast things on a two-dimensional celestial sphere and work with 2D stuff, then it looks it's non-unitarity. It doesn't satisfy the unitarity bound, and this is sort of an operator that is not normally considered in CFT, so that's novel. And there are many more operators that have conservation equations with higher powers here that are part of the game, but that don't normally show up. And so this is one of the stark contrast to textbook 2D CFT that we have to grapple with, because we know that these symmetries are there. We spent several hours deriving BMS symmetry and then convincing ourselves that this is actually a symmetry of Einstein gravity by relating it to memory effects and soft theorems. So this is robust. Okay, so much about this operator. Then we had the sublinks of graviton theorem, which had, so this was this guy over here, this one, where on the right-hand side, there was omega to the 0, and this omega to the 0 actually corresponds to a pole at delta equals 0. So we move the 1 over delta pole to the other side and define a new operator here, this guy, which has this correlation function. We didn't like that. That didn't look like something that we recognize. So I did something behind the scenes and then told you the answer that I like. Let me now unpackage this a little bit. So we don't like this. We don't really know what this is, except if we are a CFT person who has lived in CFT land for a long time, then you can recognize this. But we are more pedestrian here, so we don't know this. So what do we do? Well, I told you yesterday that there's a certain smearing on the sphere that I can do to bring this in a nice form. That smearing has a name. It's called a shadow transform. And it's a transformation that appears over and over again in 2D CFT. And in particular, in places like conformal bootstrap, it's a very useful transform to have around. What it does is it is an integral over the sphere. So Z prime is the angles on the sphere. And then it comes with this extra factor here. And the powers here involve the conformal weights, h and h bar. And remember, those sum up to delta, or the difference to j with some, yeah. Okay, so if we hit now this correlator with this transform, sticking in the h and h bar that this guy has, then we land on this equation. Let me tell you another thing here. So what happens to the operator? If you do a shadow transform on an operator that has dimension delta and j in 2D CFT, it maps it to an operator of dimension 2 minus delta and minus j. In arbitrary dimensions, this would be d instead of 2, so the dimension of the sphere. So what happened to this dimension 0 operator? It became a dimension 2 operator, and the spin flipped. And then the correlation function takes this form. And if you have taken an introductory course to 2D CFT, you will recognize that the right-hand side here looks like the right-hand side of a stress tensor correlator. And this motivated to say that this object here should actually be our stress tensor. So, okay, let me do this first. So I'm going to define this operator to be the stress tensor. Well, let me just call it O soft first, O soft 2 and 2, and identify this with the stress tensor. And then you can work out that when you hit this with, and by the way, this is the h's of all the other operators, right? And in a momentum basis, if you remember, we had this operator omega d by d omega, which we got rid of and turned into a number by going to the boost basis. So you hit the right-hand side now with anti-holomorphic derivative, and you get the familiar conservation law for a stress tensor. Oh, we talked about this yesterday. So you have to Exactly. So, well, you will get rid of all the omegas because the Mellin transform takes that away. But you can look at how this happens. So you have to work out what this means. And you can do that. So this will give you H. Okay, good. Yeah. Yeah. Excellent question. Excellent question. I recommend to shadow always. So what we have, so for these two guys here, it turns out, well, there's an operator of dimension 1, and there's another operator of dimension 1 for spin 1 and spin 2. Now what happens when you shadow that operator? What does the dimension become? And what is d minus delta in two dimensions? 1. So we have an operator of dimension 1 which shadows to another operator of dimension 1. And that's the reason why here we did not need to shadow, because we already had an operator with dimension 1 and it had the right structure. If you shadow this operator, you will get another operator with dimension 1 and the spin will flip. So what is that in terms of, let's say for the J here? If I take this operator, shadow it, there's another operator of dimension 1, but now the spin is flipped. What do I do on the right-hand side? What do I call it? Yeah. So it just so happens that the symmetry structure for the leading and for the leadings of photon and leadings of graviton theorem is symmetric. There's a picture that I could draw, which looks like this, where you have J on one side, J bar on the other side, and going between left and right is doing a shadow transform. Now this picture has a meaning. Here I take C derivative, here I take C bar derivatives. So then when I take a C bar derivative here, I get to the conservation equation that I wrote there, del bar J, 0. Or I can go from the other side and I get del J bar equals 0. So this is called, well, the structure is a conformal multiplet. You could put an operator at the top, which I could give some name. And the name that I give it here is not arbitrary, because actually it turns out that for the free boson that you might learn in 2D CFD, this is the structure. So if you start with the free boson and you hit it by derivatives, you get currents. And then you hit it by the respective other derivative, and you get this conservation equation. So you can then work out, just using CFD tools, there's no more reference to the bulk. You can go use your CFD toolkit and ask, well, what is this structure for all the possible soft operators that I have? So you start with all soft terms up to infinite subleading order if you like, and you try to extract, well, is there some special operator in the 2D celestial conformal field theory? And you do this by asking what is the structure for all these other soft operators. The soft operators will typically go to the left or right of these diamonds, or sometimes they start on top, and you have to figure this out using conformal representation theory. So once you have told me that, look, in my S matrix, there is special stuff that is going on that smells like it's universal, because we talked yesterday or the day before yesterday, that in the soft theorem, these soft factors depend only on the momenta of the other particles. They do not depend on the theory. So for the leading and subleading one, this is true. For the sub-subleading one, you have to say a bit more to extract something like this. But from the CFD point of view, I don't really care. I just know that when you take delta to integers, something special happens. Now I know that operators with delta are special. Let me look at what the symmetry structure is. Let me look at what these conformal multiplets look like. And if I find conformal multiplets that close like this, that shorten like this to some conservation equation, I know I've succeeded. I found symmetries in the conformal field theory. Yes? Indeed, it does. So you might ask another important question in this whole holography context is, what are the local operators? So if you didn't know about this fact that after the shadow you get the stress tensor, and stress tensor is something you like, something that you think is local in CFD, you might have thought these are local. But now what it looks like is actually that you should shadow everybody, and the stuff that you started with may be interpreted as a non-local operator that takes you to a local one. So there are open questions. So these are open, we are now in open research territory. Like, what does all this mean? And do you need to shadow? What does the shadow mean from the point of view of the S matrix? It's a transform on the 2D sphere. What does it mean?
the bulk of so the boundary operator is the shadows of the bulk points.
There is some recent works by Shiraz Minwala and collaborators, together with recent work by Shamik Banerjee and that go into this direction, that sort of work out how the shadow transform actually naturally arises if you think of the S matrix as a boundary correlator, like in ADS-CFT. So yes, I think that's the right answer. But just starting from the S matrix without knowing about ADS-CFT or whatever, you found it like that. Okay? Yes. Yeah, I mean, so you can classify in CFD how the structure looks like, just starting from the soft operator itself. I was at first thinking of actually doing that in detail, but then decided not to. Well, if you prefer, we can do it, but let me just give the short answer now. The word that you're looking for is primary descendant. So if you start with a primary, so these two are primaries, and you find descendants that are also primaries, so let me put these dots here. Dot means primary. If you look at this so this is the photon. If you look at the graviton, you have something similar like this, but I will remove these dots here, because if I start with some operator up there, or let me just start with this O delta 1, 2, O delta 1 minus 2, soft. And now I take derivatives. Well, I told you have to take two derivatives to make this 0. So there's one, and then there's another one. And that one gives this conservation equation. So the del square O is 0. But if you just take one derivative, you hit a descendant, and that was this P, right? That P is not a primary, but once you hit it again, it becomes a primary that is a descendant, which is 0 up to contact terms. So what was your question again?
If there's an interpretation of the symmetries.
Yeah, so the symmetries you know by taking the soft theorem and mapping it to here, and then you figure out what is the, okay, so good. I have to say a few more words to answer this. So the operators that I've written down here are soft operators. In the first couple of lectures, we talked about BMS symmetry, superpositions, and their charges. And then in connecting to soft theorem, I told you it's useful to connect the charges into a soft part and a hard part. And the soft part corresponded to inserting a soft particle, and the hard part was the right-hand side, which we didn't talk much about because it's messy. So these operators here are the unsmeared soft charges. So if I take them and I smear them over the whole celestial sphere, then they become precisely the soft charges that I talked about the other day. Now what about the hard charges? They have to be there too. And we said soft plus hard in the future is soft plus hard in the past. And that's the soft theorem. So I've here the soft theorem. Where's the hard charge? Well, the hard charge hides in these factors here. It hides in, so this is the hard charge applied to the states on the right-hand side, to the matter. Tells you how, so if you act with the hard charge, then this will do the symmetry transformation on the hard particles. And the symmetry transformation on the hard particles, if you massage it long enough, will take the form as this. So here you have the hard particles and there, and then the action of the symmetry transformations, BMS, superposition, and so on, will spit out for you these factors. That's how it works. It's a longer computation that's not very illuminating, so I'm not doing it. One thing to point out here is how does BMS act? And first of all, how does translations act? So translations are part of super translations, so they are part of this guy here. And if you remember, well, the momentum operator, it has some factors of the energy, and then it has some direction. This was this Q that we have written down, this null vector. If I Mellin transform that operator, and the Mellin transform has omega to some power that involves delta, well, if I add another omega, that shifts, so then delta minus 1 gets another omega, so it shifts the delta that you have after the Mellin transform. And so what this means is that the action of translations, because it involves the fact of energy, will do something to the hard operators in your correlator. So if you have the momentum operator here next to hard operators, if you think about taking the OPE of these operators, what it means is that not only do you get like this stuff here on the right-hand side, but this momentum operator also acts on the dimension of the hard operator. And I've written this down here. So this is this +1. So action with translations or super translations will shift the dimension of the hard operators when you take OPEs. Yeah. Sorry, what? Here? On this side?
No, I mean the middle of the square.
This? What do you mean middle of the square?
Okay, so you're taking the bar on the left and then the on the right.
Yeah.
So on the top level,
Yeah.
on the very top,
Yeah.
if you take a D bar and then you take a D.
No. So here we are looking at the structure. So I'm writing down the relevant structure that gives the symmetry. So you can take derivatives and then you get descendants. But here, in taking enough descendants, you hit another primary. So that's what I'm drawing. So if you take enough descendants here, you act enough with del and del bar, you hit another corner, and that corner is a primary. So that's the relevant stuff that I'm. Otherwise, could write down crazy descendants. Who cares? I'm interested in the primaries. And sometimes descendants become primaries, and that's precisely when you have this thing shorten and become a shortened multiplet, and this has to do with symmetry. As you can see, as a conservation equation, something is conserved, there should be a symmetry. Okay, so where was I? Yeah, so I guess I wanted to sort of go through this again to highlight it's not hard, not that hard. And we can see that there's some shadow transformations that go on, and you see that in order to get a stress tensor into the CFT, you had to use that, and you can use a shadow for the other ones as well. And there's more recent interpretations that that's actually the natural thing to do, as you pointed out, and as was shown by Banerjee based on the work by Minwala in the last months. So this is very much at the frontier of research. And okay, now, great, are we done? We have photon theorems of graviton, leading and subleading. We have found that there are special operators. So, well, this guy, which unfortunately doesn't have we didn't give it a nice name, but it has this conservation law, this, and this. I actually erased something which I wanted to write, but if you stuck with this operator here, which had dimension 0, that would be, well, it's the shadow of the stress tensor, right? It's the shadow stress tensor. Sometimes that's a thing that people think about in CFD. But it doesn't have this conservation law. It has a much more complicated one. Well, actually, not so complicated. It's kind of like this one. It's 3 derivatives, and then it's 0. So 3 derivatives like this, because this was negative spin, so it's actually it's a shadow of the stress tensor, which has negative spin. And so you have to hit it with holomorphic derivatives. And these two are the kind of encoding the same information.
So tilde is the shadow of the T?
Yeah, that's just the definition. Tilde is what I define as shadow. And yeah, so it's just a shorthand. And if you want to know how this looks like as far as the conformal multiplet goes, well, here I told you, well, you could shadow and then nothing would change. This is symmetric. So this just exchanges left and right, and it's symmetric. Involves 1 or 2 derivatives. Now for the stress tensor, it's not symmetric. You get something that looks like this. So here sits our stress tensor. Here sits the shadow stress tensor. They're related still by a shadow transform. So this is still the left and right relation. We know that when you hit T by del bar, this gives 0. So this is this direction here. There's another primary at the bottom here that is also a descendant. And then here, well, you have to go 3 times. So there's actually descendants that you hit which are not primaries. So I remove those dots. And so this is also del cubed T tilde. And you can figure this out. The only input that you use is that there is a soft thing going on in the bulk. That gives you the delta that you should look for. I told you these are integers. And now you go and run your CFD toolkit and figure out all these guys, all these celestial diamonds, we refer to it. And this is the power, this is what I was referring to the other day, is that it's really in these boost spaces you can exploit your CFD tools, and 2D CFD is very powerful. You can exploit your 2D CFD tools to get quite a lot of mileage. And the mileage is that we can figure out what all the special operators are and how their multiplets look like. Okay, so are we done with these sort of three guys and the shadows? Is that all? Well, I just told you that in principle we could go on in the soft expansion and see if there's more. And indeed, there is more. So let me just illustrate this. So what about sub to the n leading soft theorems or soft operators that we extract? So at tree level, I told you that if you take an n plus 1 point amplitude, then on the right-hand side, you get a Taylor expansion, and now let's write down the infinite sum. So omega to the n, starting with n equals minus 1. And then let me remove the n point amplitude to the other side, so I divide by it. Okay. Yeah, let's do that. So for the leading and in gravity, for the leading and subleading soft theorem, this is an equality. For more subleading soft theorems, there's dot, dot, dot. And in this dot, 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 what that means is that, so this piece, if you only had that, then we would have a true factorization between n plus 1 and n point amplitudes. But because of this dot, 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 it means that at some point in the soft expansion, this factorization fails. And you can't just write the right-hand side as an n-point amplitude. There will be other stuff. And so this other stuff will have to do with the fact that there's some non-universal contributions. Now, in this dot, 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 depend on your theory. They don't depend just on the momenta of the hard particles. They depend on the theory. And there's also loop corrections. So these are not tree-level exact. We'll talk about that in a moment. But let's ignore this for the moment. Let's ignore this and let's look at this thing for infinite n. So it turns out that if you do this, you can actually extract an infinite set of operators, and this infinite set of operators can be shown to satisfy an algebra. And now you should be like, whoa. There's an infinite list of operators in gravity, Einstein gravity. And that infinite list of operators obeys an algebra. Whoa, okay, great. Okay, so infinite dimensional algebra. How do we see this? Well, to see this, I should introduce something else that you probably, some of you may have had in mind, like, does this exist in this celestial CFD? What kind of other tool data do we need in CFD? We have now operators, we know the ranges of deltas. What is the thing that we need in CFD to sort of solve theories or like determine theories? OPE. I haven't talked about OPE yet. Where is the OPE? I mean, I mentioned it before, but I didn't tell you what it is. So how do you get the OPE? What does it mean? So if I have a CFD, what does it mean to take the OPE? How do I take what is an OPE? Yeah, or some other operator with some operator. And what does it mean expand? Expand in what? It's when you take the two operators close, right? So what does it mean from the bulk point of view if on the celestial sphere I take two operators close? If I think about my original scattering amplitude, what happens to the particles? Collinear, they go to the same point, right? They become collinear, the momenta become collinear. So I have to talk about collinear limits and how this becomes what we call celestial OPE. Okay? So let's do that. And this is actually rather easy, much easier than all this like soft discussion that we have been doing. Okay, celestial OPE. So again, we focus on tree-level amplitudes. For the point of illustration, I'm going to use massless particles. And we're going to take the collinear limit. So I'm going to have an amplitude that has some amount of particles. 2 of them will become collinear. So we want to do this for gravitons at the end of the day. Yeah, let me do this for gravitons. So there's a graviton with helicity Li. Next to it, there's a graviton with helicity Lj. Then there's other particles. And then we have the momenta, the one with Pi, the one with Pj, and then the other guys. And now we want to have Pi goes collinear with Pj. Now it turns out that, well, this is something that one wants to study for the S matrix, so things have been worked out. So we can describe the right-hand side. Okay, let me write this down. So we can describe the right-hand side of making these 2 guys collinear by there's some factorization. So there's some splitting function, is it called? Some splitting function that depends on the helicities and the momenta of these 2 particles that we take collinear. And then it also depends on the helicity when we make these 2 particles one particle, so to say. So that's L. And then this comes with the amplitude where we no longer have these 2 particles, but we have one with helicity L and momentum P. So where do these collinear divergences come from? They come from the propagator, right? So yesterday, or the day before yesterday, when we talked about the soft theorem and I wrote down something, somebody said collinear limit. Well, it looks very similar, right? So we have this Pi plus Pj propagator. And in this limit, this just becomes, we're talking again about massless particles. So Pi dot Pj for massless particles is what this is. And it has been shown that this has a universal form, which is why I wrote this function here. And it can be derived by looking at 3-point vertices. So I'm going to assume that somebody did this for us, and we're now just going to take it and see what the celestial OPE becomes. So what does it mean? What does Pi collinear Pj mean in this celestial parameterization that we have used the other day? Well, you don't actually have to remember because you can just think about what we have written upstairs. If I have an operator inserted at Zi, another operator inserted at Zj, and I want to take the collinear limit, what do? Zi goes to Zj, right? Let me denote this as Zij equals Zi minus Zj, and that goes to 0. Okay? So I have the celestial sphere. This is my I guy, my J guy, and I want to take them close. And from the amplitude point of view, this is stuff goes in, and let's say these guys are I and J. I take them close. Okay? Is this all that I can do? So if we work in our familiar 1,3 signature, then, okay, you can discuss collinear limits, but in gravity there's no collinear divergences, so we couldn't do anything. So there wouldn't be anything, any OP to extract. Okay? Then what now? So it turns out that it is very useful both in amplitudes, for amplitudes purposes, as well as for celestial conformal field theory, to move from 1,3 signature to 2,2 signature. We complexify the momenta. What that means is that previously Z and Z bar were related by complex conjugation, but once we complexify the momenta, they're independent. So 2,2 signature, they're no longer the same. So let's do that. Let's go to this other signature. That turns out to be very useful because there are certain 3-point celestial amplitudes that we can write down, which would be 0 and the 1,3 signature. So there's some stuff that we can study with this. So when these are no longer the same, there's something else that we could do here. Say it? Z bar, exactly. So there are two collinear limits that we can take, and this is the holomorphic collinear limit. So we can take either one. And so this pi dot pj in the holomorphic collinear limit becomes just 1 over zij. Okay? And so now let's write down the celestial OPE that comes from the collinear limit of two gravitons in the amplitude.
I'm sorry, that was a bit fast. Can you just repeat,
Yeah.
what's holomorphic and when you use the...
Oh, that just means that you take the zi to zj, and the anti-holomorphic is you take z bar I to z bar j. There's nothing deep, it's just the z holomorphic coordinate, z bar.
In the two signatures, the two are independent.
Yeah. That means that you have two independent limits. So you can take zi to zj, holding the z, keeping the z bars untouched, or the other way around. And those will give two different, one will give this, and the other one will give that. Yes? Two different celestial OPEs, two different collinear limits. Yeah. So there's just two limits that you can take now. And for gravity, this turns out to be relevant because otherwise you wouldn't have any OPE. In gravity, you have something like z over z bar. So if they are related by complex conjugation, well, if you take one to 0, the other one goes to 0, so there's not a pole. And the OPE has a pole, okay? So if we take them to be independent variables, then we get a pole in one of them, okay? So let's say you are, let's say the particles are outgoing, the ones that you take collinear, then they both end up on the future sphere. So we are outgoing, we are at future null infinity. Then on the past boundary, this may be antipodally related, but if they two go on the same boundary, future or past, then you don't have to worry about that. Okay, so let me give you the splitting function for gravity, and then let's work out what that means for the OPE. So to extract the OPE, we compute the Mellin of the collinear limit. So in general, we would have to let's say, we have n particles, we have to do n Mellin transforms, the omega k, I'm just writing it differently than yesterday, doesn't matter. Then there would be our n-point amplitude, so L1 to Ln, and in there are the two guys that we want to take collinear. So those are all the guys. Now we take the collinear limit of that. So let's not do the integrals yet. Let's first do the limit. And then doing the limit, this corresponds to taking Zij to 0 of the Mellin transformed amplitude, which means I will call this M instead of A. And then these guys will depend on so the helicities become the 2D spins. That's the same thing. And then instead of the momenta, I will write delta 1, Z1, Z bar 1. These are now independent. Delta n, Zn, Z bar n. Okay? Now, it turns out that we don't actually have to do n Mellin integrals. That would be rather horrible. It turns out that we only have to look at the two guys that we take collinear. Okay? And to see this, we're going to do a change of integration variables. So what we're going to do, and this is something to work out, I'm just telling you. So let's take each of these omegas. Actually, we only have to take the ones that we want to take collinear. And we take it to be, the ith one we take to be alpha omega p, because this will be related to the momentum after the collinear limit. So here's just a name. And then the other particle that we want to take collinear with the first, we do this. Okay, so this is just a change of variables. After we do this change of variables, this whole product of Mellon transforms, whatever, will contain a piece, which is the only piece that we have to care about to extract the collinear limit, where now the omega I, omega j integrals are replaced by omega p and alpha integrals, right? So this is now omega p. The delta here becomes delta I plus delta j. Then there's this 1 over omegas upstairs, and then using the way that this transforms, I will get one extra factor of omega here. And then I could get potentially some factors of omega from the way that the splitting function depends on the energies. So this I don't know yet, so let me put the hashtag here. Then there's other stuff in this integral, which I don't have to care about, because I'm just focusing on the collinear limit. And then there's this alpha integral, which goes from 0 to 1. And there will be factors of alpha and 1 minus alpha from the change of variables. And they will depend on they will have some exponents. Let me call it x minus 1, y minus 1. And the x and the y, this will also be determined by the splitting factor, whatever this becomes in the collinear limit. So this piece comes from the split, and these guys as well. But without telling you what actually this collinear limit is, you can now tell me what the celestial OPE is. The thing that we have to focus on is this integral. Does anybody know what this integral is? Fantastic. You see, this guy shows up everywhere. This is the Euler beta function. It's given in terms of products of ratios of gamma functions. And this is the structure of the celestial OPE. So let me write this down for a particular case. So this will be a homework exercise for you. In gravity, where we take two positive helicity gravitons, so Li and Lj are plus 2, the total helicity of the particle that we replace the two collinear ones by will also have 2. And then there is Pi and Pj, so the first and the second. And this takes the form, it's very simple. Doesn't fit in this line though. So there's a factor of the coupling, because I told you can figure out the split factor from the vertices, and the vertices will have a factor of Newton's constant. So there's a factor of kappa. And then there is a z bar, ij, and over a zij. And so you see that if we didn't have the holomorphic and anti-holomorphic collinear limit, then there wouldn't be a pole. And then there's some factors of the energies. So this omega p squared, the final particle, and omega I, omega j. Now you take that, plug this in here. When you recast it in a form with this Mellon amplitude, you can read off what this is, and what that is. Okay? You have all the information. All is in here.
So this split is the individual, it's like a factorization of the...
It's a factorization of the amplitude from two particles that go collinear with momenta pi bj, helicity li lj, which becomes a party of momentum P and helicity L. Yeah.
So when we go to two signature, we can take holomorphic and anti-holomorphic independently.
Yeah.
Then when we want to go back to 1, 3, we should end up with the same.
Yeah, so if you are stick with 1, 3, then you don't see the structure. So,
We would want to go back to 1, 3.
well, it depends. I mean, sometimes there's structure that you see if you go to sort of special limits, or you know, you split things in certain ways and then you see some structure. Let me point out, so there are some people here that study twistors, right? The people studying twistor theory, no? Yeah. So this is something very naturally connecting to, you know, twistor variables, going to this 2,2 signature. And indeed, in this whole celestial holography program, there has been some collision of different fields. So we talked about amplitudes, we talked about GR, we talked about conformal field theory. Twistor theory also enters here. Then there's something called twistor holography, which I'll mention in a second again. There are different fields that collide. And so different aspects are very naturally described in some of these languages. And celestial OPEs is one of them. They have a natural place also in using twistor variables for amplitudes. So let me write down the celestial OPE now. So I've given you the split factor, it's this guy. I told you how to take the collinear limit and then the Mellin transform. You can work this out now. We already established that we have this Euler beta function. So once you stick this in, the thing that you will figure out is what this x and y is. And that will tell you what the OPE is. So if you take a graviton, a hard graviton, so I keep delta whatever, and let's say we take positive helicity, because this is the split factor that I wrote down, at Zi, Zji, so this is delta I guess. And then another graviton, delta j, also positive helicity, at Zj, Z bar j. Then this behaves as follows. There's a factor of kappa over 2, minus kappa over 2. There is this collinear singularity, Z bar ij over Zij. So the Zij is the singular part. And then there's this Euler beta function, which if you work through that calculation, you find that x is delta I minus 1, and y is delta j minus 1. And that guy comes with an operator on the right-hand side, which also, so this upstairs 2 in the split factor is the total helicity. So this has spin 2, Zj, Z bar j. And what is the delta? Well, the delta is actually the sum of delta I plus delta j. So you have now learned that the celestial OPE, the OPE in celestial conformal field theory, whatever that is, whatever the theory is, you have written down a proposal for what the OPE is. Okay? Yeah, you can, okay, so here this is just for the primaries, but then descendants come also in, and then you will write down an infinite sum of primaries and descendants, yes. But that's for the leading one, that's for the singular part. So the singular part has the primary in it. And then the other ones are regular, yeah. Yes? Yeah, it's dependent on, like in CFT, you took I to J or J to I. What do you mean? There we just didn't, this is usual CFT, except what's different from usual CFT is that, okay, here's this particular structure with the Euler beta function. And we have some anti-holomorphic dependence in there as well. And then there's also a tau of descendants. And I wanted to end on this note here, because what happens now, maybe let me write this down as well, because this is the wow. So now I've told you two things. I've told you about the soft limit, and we saw explicitly that some of these soft operators are symmetries that we discussed in the first part of the lectures. And now I told you what the OPE is. With this, yes?
Like in CFT, there is a correspondence that ensure that these OPE
This is a very good question. Conversion of the OPE. There are some important open questions about the celestial OPE. This is part of it. Yeah. There is a proposed state operator correspondence, which involves the shadow transform. But the structure of asymptotic flat space is so intricate that I think there is no like common final like textbook status of agreement on all of these questions. Yeah.
How do you even define state operator without a message?
Well, no. So we can do okay, I did not go into this, but, and you didn't ask in the discussion session how you go from Lorentz to global conformal. If you had done that, then we would have talked about the generators in the 2D conformal theory. So we have the L0, 1, -1, and then everybody else, global conformal generators. And then you could have asked me, well, what's the relation between Ln and L bar n, or Ln and L minus n, and we would have found that it's not the relation that you find in your usual 2D CFD textbooks. And what enters in that relation is a choice of inner product. And yesterday we talked about Klein-Gordon inner product. So if you choose that, you land on the conjugation relation between the L's that is not the standard one. But if you use, as your definition of the inner product, a shadow transform of one of the guys in the inner product, then you do land on the natural conjugation relations. And so this is another hint why you should do shadow transforms. And then once you have that, you could run your usual radial quantization game. But there's various like basic questions that are still sort of not completely resolved, and so not all these questions that we in CFD are sort of as a given are part of our setting up CFD are still open questions. So there's something for you to do. They're like basic questions that still need answers. Okay, so now let me just write down the symmetry algebra that you get from these infinite guys here. So we think of a discrete family of conformally soft operators. Let me call them H now, so these are my gravitons. And K will be the dimension. And before we used like the limit of delta minus 1 times the operator blah blah, let me write this now in this form. So I take limit epsilon goes to 0, epsilon, so this is like the delta minus 1 and so on that we've written down before. And then I have an operator of dimension K plus epsilon plus 2, where K is like the conformal dimension. It starts with 2. This guy we have never talked about. It kind of has to be here, but don't worry about it. So there's a 1, there's a 0, minus 1. These are the guys that we talked about, these two. So this operator will have weights H and H bar, which look like K plus 2 over 2, K minus 2 over 2. And we can write down a mode expansion for this operator. Well, I guess I wrote this down like this. So this depends on Z and Z bar in general, and I can write down a mode expansion. So modes n that are just holomorphic, and then I have also the anti-holomorphic ones. N plus K plus 2 over 2, or K minus 2 over 2. And this sum runs from K minus 2 over 2 to 2 minus K over 2. Okay, looks random. So normally in CFD, what you see is like you expand, let's say, from m equals 0 to n minus 1, or somewhere, to infinity if you wish, and you have an expansion like this. Okay, so this is what you normally see. The only thing that I've done here is I have shifted that m. I've shifted that m to K minus 2 over 2, and then it runs until here, instead of until some finite value, and this is how I wrote this down. This is a choice that will turn out to be convenient in a moment. Because once I've made this choice, and I start with these modes here, I can write down the commutator of these modes. So commutator of these guys here. What is a commutator? In CFD, a commutator has to do with OPE, right? So the commutator of the generators is the OPE, comes from the OPE of the operators. So These are our operators. The O's is what I call now H, shorthand. That H we expand in modes, and then the OP of these H's would tell me about the commutator of these modes. Okay? Yes? Oh, so this is something that I'm telling you now. So first of all, when I wrote it like that, there was a finite n, and this finite n had to do with this symmetry structure from these conformal multiplets that you can work out in CFD. Right now I'm telling you, look at this finite range, this discrete set of, it's a wedge, right? It goes from, there's a wedge of operators. Let's look at that wedge, and let's see what the commutator of that wedge is. So this is, yeah, okay, why do you think about this? Like, huh? But you will find that actually there's something that comes out of this. Okay? All right. So, okay, I've given you this mode expansion, and now I'm telling you something crazy. I'm going to define a new mode based on these H's. So I guess this should have been K, but I guess it's N now. So let me just label these, yeah, sorry about that. Okay, the N is the K upstairs, and the N upstairs is minus 2P plus 4. Okay, that sounds crazy. Let me be a bit more crazy. Let me put some crazy factors here. P minus N minus 1 factorial, and P plus N minus 1 factorial. Sounds like a crazy choice, right? Turns out, if you look at modes, these modes that we have written down here in this wedge from n equals something to something, and then you multiply these modes by these crazy factors here, then it turns out that the OPE of these guys is something nice. Where does it come from? Well, it comes from taking the OPEs of those H's, so you plug in what you've learned upstairs about the OPE for gravitons, plug it in here, and then read off what the commutator is. And that commutator looks like this. This is the commutator of an infinite list of operators with modes inside a wedge, and it takes a one-liner. What do we say now? Wow, right? Isn't that crazy? It's crazy. This is called, this has a name, it has been discovered before, before all this celestial story. It's called W1 plus infinity algebra. Actually, it's called HAMZ2 algebra, I'm told by my twister friends. And then you have to add some condition on Hamiltonian vector fields on C squared, and then it becomes W1 plus infinity, but that name is stuck, so that's what it is.
So this is the algebra for the real sorrow.
No, all of them. So all of the infinite list of soft operators in gravity, starting with dimension 1, dimension 0, dimension minus 1, infinite, semi-infinite list. You mode expand, but use the wedge, and then you find this algebra.
So I suppose you also need to write down the Puhm,
Okay, very good. That relates to these other questions about the OPE. You can ask, is the OPE associative? Does it satisfy Jacobi? Pick your theory and verify if it does or doesn't. Sometimes it doesn't, and then you either despair or you try to fix it, and sometimes you can fix it by adding other fields to your theory that fix it. But there's also an open question in general, like, is this some condition that we should impose? So for example, we could say celestial amplitudes is another, so okay, there is S-matrix bootstrap where we try to find the non-perturbative S-matrix based on some general principles, axioms, symmetries, and so on. Now we have another object called the celestial amplitude, which is nothing but the S-matrix is another basis. Can we use sort of CFD constraints, because this is supposed to be an object in some CFD? Can we use constraints there to infer what kind of theories have a good UV completion? This is something that you can ask. So something that you may want to try to ask is, well, let me impose that the celestial OPE should be associative and satisfy nice properties. And if a theory doesn't, then it's not a good theory. Turns out that in some of the good theories, by good I mean have a good UV, like some string theory, this is nice. In some other theories, it may not. I will say something else in a moment that relates to these questions of connecting to the UV, but let me just remain here for one more minute or so. Yeah, what did I want to say? What did I want to say? That was a question. I think I lost my thread. Okay, so we have the celestial OPE. There are lots of questions about it. But if you just take what I told you here and you work through this, then you find that there is an algebra that's obeyed by an infinite tower of operators if you mode expand in that wedge. And let me make a comment here. This wedge has to do with the fact that the symmetry parameters for your symmetry transformations have to satisfy conservation equations. So del bar j equals 0 implied that del bar epsilon is 0. But from an asymptotic symmetry point of view, this could have been an arbitrary function of z and z bar. Similarly to BMS. In BMS, there was some function that was arbitrary, but we found that we had an operator that should be conserved like this. And so this function that we had the other day, that function f, also has to be conserved like this. This has to hold if you want to look for bona fide symmetries in your 2D theory. And I come back to the statement that you have to define what you mean by symmetry. Asymptotic symmetry is not the same exact definition as symmetry in 2D QFT or 2D CFT. And so these conditions have to do with the restriction to the wedge here. And so what we did here, now you use your CFT toolkit, you find all the symmetries. What it means is that symmetries that satisfy such conservation equation. This will give you lots of non-unitary operators that have to do with symmetries. And the parameters have to satisfy certain conditions. And this ties with this wedge condition. And then you get this algebra here. And now there are questions of, okay, what does this algebra mean? Does it constrain your theory? How powerful is it? And so on and so forth. And these are open research questions.
Sorry, can you just explain a bit the notation because I got lost?
Yeah, that is a crazy notation. So here we have so that k was the dimension, that n is the mode number.
So the k is the
Delta.
delta.
Yeah.
For the order of the subject vector, right?
Yeah, and that epsilon was like multiplying by delta minus 1, but I've written it in that way so that I can capture all of them at once. So we had before like factors of delta minus 1, delta plus 1, and so on. I wrote epsilon so that I can capture all of them at the same time. And the way to do that is by adding this here in the delta. So before we had O delta, we had the delta minus 1, we had a delta plus 1. I just repackaged that so that I can write all these special operators in one go. So you can read off, those all have different dimensions, but they all define soft operators. And then I said, well, let's define something crazy. So this is like that H up there, but with extra factors. And you might ask me, well, is there a meaning to these extra factors? Okay, not. Damn it. Yeah, sorry. That n becomes that p, that k becomes that n.
Okay,
Yeah.
so the position stays. Okay,
Yeah. And now ask me where do the crazy factors come from? These crazy factors actually come from half a shadow transform. Half a shadow transform. Or square root, or whatever you want to call it. So instead of integrating over the whole sphere with these crazy factors, 1 over z to some power h and so on, we do now something called a light transform. A light transform is sort of a holomorphic shadow transform, or an anthomorphic one, so we integrate only over z or z bar. And when you do that, you get these crazy factors. And so this is another thing, so having this nice, okay, this is beautiful. So this is sometimes symmetry. Symmetry principle is beauty. This is beautiful. So it means that we should include these shadows or light transforms to get to that. So that's another reason why this is good. Yes?
Why don't we also study the operators of higher order integers?
Oh yeah, good, we do that. So This includes delta 1, 0, -1, -2, blah, blah, blah. Is that what you mean? You could ask me something else here. What happens above? Good. So actually, if you take a shadow transform, then you can capture also the operators above. But those contain the same information because whether I have the operator or its shadow, it's the same thing.
And this only for 2D
For higher dimensions, you also have a list of soft operators. But as I remarked the other day, you don't get local enhancements of symmetries. But you also have a list of soft theorems exist in any dimensions on the formula that I wrote down. The P you can write down. So I have P mu's. Just take mu to be, whatever dimension you like. They're the same. Yes? Ooh, good point, good point. Yeah, what does it do with this, right? So what's said here is that, well, there should be a universal part of all this soft tower. That is this. And indeed, because we have used, in order to write this down, we used the OPE. And the OPE has a leading order pole. Then it has plus dot dot dot, and that plus dot 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 will contain regular stuff. And it's the non-universal stuff does not touch the singular one. But it comes in later. And actually, I have an ongoing project in sort of figuring out what all happens with that regular stuff and so on and so forth. That one? I think that one is that 2 over there, which I haven't talked about, which somehow you have to include. It decouples. It doesn't do anything, but somehow you have to include it such that this algebra closes. The k equals 2. So we never talked about the k equals 2. I mean, we did, but the k equals 2 that we talked about for the stress tensor was the shadow of that 0 and not that 2. Okay? So this is kind of the center, and this is kind of the 2. I'm not really sure what else to say. So this is just a name. Sometimes people call it W infinity, but I guess it's the more proper name, and even the more proper name is what people call HAM-C2. Whatever that, if you know what that means, you know what it means. If you don't, yeah. Okay. So then, where was I? So, okay, good. We have now this infinite dimensional algebra, and now you can ask what does it mean, and so on and so forth. Now let me finish off this infrared part with a couple of comments and then connect to the UV. Okay, so we derived the celestial OPE. There's open questions with that. Somebody asked me a question after the lectures yesterday that I would like, again, to be raised in this course. How am I gonna make you guess this question? Okay, so in CFD we have the operators with their conformal dimensions, list of operators. We now have OPEs. What else is important to characterize CFDs? Central charge, yeah, so what is the central charge? The short answer is we don't know or we don't agree. How do you get that? Can anyone guess how we would compute with the tools that you have learned now what the central charge is? Yeah, but how? Like, OP of the stress tensor, good. So how do we compute this with the tools that you have learned now? Yeah. Or, I mean, if you take dimension 2 operators in there, you kind of already have the OPE. So we can infer this from collinear limits. Collinear limits of amplitudes with 2 gravitons. And those 2 gravitons, we give them dimension 2 in the boost spaces. So that should give the OPE. It turns out that the leading term here, well, let's say Z and W. Yeah. So from this you would infer 0, and then you cry and go home. There's no central charge. Maybe a friend comes and consoles you and says, well, maybe it's not so bad because in flat space there's no scale. So maybe that's what you should get. there is, so, and let me say here that this comes from looking at collinear limits of tree-level amplitudes. So maybe if you do the full computation or something else. There's other computations that said that C should be infinity or I times infinity, which, okay, maybe that's also fine because, again, there's no scale. But the bottom line is this is still not a settled question. So that is another thing for you to do. Okay, that was that. And now I need... Times what? Oops. Yes, you could try that. There are many things that you could try. Then tell me what C is, and let's discuss whether that should be the right answer. I don't know what the right answer is at this point yet. There's another thing that you could ask. So we've derived all of this from tree-level considerations. All the soft theorems and the symmetries, even the stress tensor, we derived from sort of tree-level soft theorems. But I told you there are loop corrections. And the soft theorem that gave us the stress tensor is loop corrected. So we have to deal with that. Where is that? Okay, so loops. What about loops? Well, it turns out that this nice formula that I wrote down, which had, in principle, this infinite Taylor expansion, gets corrected. So there's not just omega n times a soft factor. There's omega n log omega to the n plus 1. And this is a different factor now. Let me call it S log. And so this is some papers that should, I think, be famous now, by Saho and Sen from a couple of years ago, who proved that when you consider loops, there's actually new soft theorems, logarithmic soft theorems, which, so the n equals -1 is the leading one, which is the Weinberg soft pole, which is, that's tree exact. But then everybody else equals 0, 1, etc., receives loop corrections and also non-universal terms at tree level. At tree level. At loop level, it turns out, although there's a conjecture for this infinite soft expansion, and the conjecture says that there should be a universal tower. So this non-universal thing at tree level becomes some universal at loop. So what this means is that this guy should only depend on momenta, nothing else, not the theory. All the non-universal stuff is in here, universal, which contains combinations of power law and log, where the n and where these exponents are not related like this. Okay? So these are new soft theorems. And these factors previously were very simple. These were like one term with momenta and angular momenta. These terms become really ugly, very complicated. And now you might wonder, well, my tree-level subleading soft graviton theorem, which had omega to the 0, gets overtaken by this log. So the leading one here would be n equals 0, which means log to the power 1. So that gets overtaken, and it comes with some ugly factor. And now the question is, does this still have a symmetry interpretation? We had superrotations before. What happens to them? Superrotations gave us the stress tensor. The stress tensor gave us local conformal symmetry. I should worry now, right? Like this is kind of where celestial CFT is built on. I should worry. But I don't want you to go home and then have sleepless nights because superrotations will not give you local enhancements. There will not be a stress tensor. There will not be a CFT, blah, blah, blah. Fear not. There's actually an answer to this. And the answer is that if you look at sort of the classical limit of these soft theorems, which remember, trees is not just trees is classical, but loops is not just quantum. Loops also contain classical stuff. So there is something that remains here, and you can understand that classical limit of this logarithmic soft theorem again as a symmetry. And the symmetry is again superrotation symmetry. The thing that you have to realize here is that when you compute your charges conservation laws, which you want to match onto this logarithmic soft theorem, so this one here, 0. So that's the soft theorem that we want to explain with the conservation law. You have to realize that you have to work a little harder to get the correct charges. And the correct charges turn out to look like this. So if you have long-range interactions, it means that particles at late times don't get rid of gravity. There's always long-range interactions. For electromagnetism, for gravity, there's long-range interactions. At late times meaning that if you go late time along null infinity, or from the time-like perspective, late time, so either to time-like infinity or to the future of square plus, these particles are not free, so there's long-range interactions. And what that means is that there will be divergences at late times that go like a log in time, which are related to this log in the energy. So if you want to construct charges, what you do, so there's a lot of stuff that you have to do, but the last thing that you have to do is you have to put a cutoff. So there's a log of some cutoff, lambda, or lambda to minus 1, which when you take this to 0, you take time to infinity. And what we found is that you can construct a charge from the covariant phase space, so run this machinery with the correct fall-offs of the fields and inputting superrotation symmetry. And on the future and the past boundary, you get charges that look like this. So there is a piece that comes with the log of a cutoff, and then there's a finite piece. And it turns out that the conservation of the Q plus equals Q minus of this piece that multiplies the log of the cutoff, that is precisely the logarithmic soft graviton theorem. So this comes from inputting that you have superrotations, the good old superrotations. If you compute the charges, you find that there is a conservation law between the future and past boundary of a particular piece of the charge that you have constructed, which is precisely this logarithmic soft graviton theorem. This other piece here, which is finite, well, it's subleading to that log term, that finite piece turns out to be precisely the this turns out to be precisely the tree-level subleading soft graviton theorem, which we had to replace by the log soft theorem. So it turns out that if you compute the charges correctly, you both get you get a charge conservation that gives the new soft theorem, which is the one that you really have to care about. And then along for the right comes a charge conservation law that gives you the soft theorem that you had to worry about. So somehow the old soft theorem is still captured in there, but the actual soft theorem, that's the important one, is captured by a new charge. And because you have a conservation between the plus and the minus guy, whether or not it's multiplied by something that diverges as you take lambda to 0 doesn't matter anymore, because you have already found the conservation law, which is this piece. So it seems that the story here is not as bad as you might have thought. The leading log soft theorem does have a symmetry interpretation. You just have to work harder to include long-range interactions in the correct way. And now the cool thing about this is another wow, is that Sahu and Sen conjectured that this piece here, never mind these ones, never mind the plus dot dot dot, but this piece here should be universal, meaning it doesn't depend on the theory. While for the tree-level soft theorem, this piece was even not universal at some subleading order. So this is really cool. Once you include loops, things become nicer. All right? Okay, I think I will not get more wows there anymore. I think we're getting a bit tired. So then let me just make a few more comments that will connect to tomorrow's lecture. So I've given you sort of the basic CFT, celestial CFT building blocks. We discussed symmetries, we discussed observables, and there were some wows in there. What's another thing that we could ask? So if you want holography, I told you we want non-trivial backgrounds. I gave you one non-trivial background yesterday that was a shockwave background. This we can describe in celestial CFT. Other things? What's sort of the main thing that we study in ADS-CFD, in holography? Or one of the main things? Black holes. What about black holes here? Well, I told you, so black holes are kind of like massive objects, right? So they go to the future, come from the past and go to the future time-like boundary. I told you massive stuff hasn't been studied so much yet, so we will have to do that in order to get mileage out of this. One question that you can ask is, well, what about black holes now? I mean, in celestial CFD, is there anything that we can learn about them? So there's not much that has been explored yet. That's a tricky question. But one thing that you could do is scattering off of black holes, and then looking at the celestial amplitudes. So you put the scatterers in the Bose spaces, they scatter on some background, which is a black hole, and then you take that to, I mean, in that Bose spaces, this will then correspond to objects in celestial CFD, so correlation function in celestial CFD, you can do that. We had a paper a couple of years ago. You might also look at some special black holes that can actually be nicely described in celestial CFD. So there are like black holes that are called self-dual black holes, which Strominger and company have studied. So they take some nice form. But then there's lots of question marks here and lots of things to explore. Another thing that you might ask is, well, you have your black hole and you have the symmetry transformations. And I told you that sort of they change the vacuum, but if you have a black hole instead of empty space, what do? So you could ask about BMS transformations acting on black hole spacetimes. And this gives rise to something that has been called soft hair. So there were papers by Hawking, Perry, and Strominger that did some BMS transformations at the boundary and found that the horizon gets wiggly, and that wiggly is interpreted as soft hair. You give the black hole a wig. The black hole is no longer bald, it has hair, okay? And we learned that the vacuum is degenerate, right? So this statement that black holes have no hair is actually not true. So that's the lower, but it's not true because we know the vacuum is degenerate. And then you could give black holes hair. And then there are some speculations about whether this has anything to say about the information paradox. And as far as I understand it, this is open questions and maybe speculative ones. You can then sort of take this and ask, well, I do a symmetry transformation at the asymptotic boundary. This wiggles the horizon. This gives you soft hair. But can you interpret this from the point of view of the horizon itself? Can you run some asymptotic symmetry analysis on the horizon? We had a paper a couple of years ago, which we called black hole memory, because now you're really asking about symmetries directly at the horizon. And there's this other law related to the no hair statement, which says that black holes have no memory. Well, if one is not true, then it means also the other is not really true, because if stuff falls in and that stuff contains memory, then by making the horizon wiggly, giving it hair, it will give some memory. But these are also open questions, like what does it mean in the context of black hole entropy, black hole information in particular, and these are open questions. Now, all of what I've told you so far is about a bottom-up approach to flat space holography. So we started with a known theory, GR, and we kicked out some new insights that are based on some old, some old stuff from the 50s, the 60s, and the 70s, and then some new insights on how they're related, and then exploiting CFD tools to say new things. So this was bottom-up. And the hope there is to find enough principles starting from something that you know. Let's say you want to identify some axioms in celestial CFD, and then start from this bottom-up approach and sort of bootstrap your way to your celestial conformal field theory. So that's related to bootstrap. You might also ask, well, is there a top-down approach? So in ADS-CFD, we have this sort of poster-child duality. You do type 2B string theory on ADS5 cross S5, and that's dual to n equals 4 super Young Mills on some 4D Minkowski spacetime. Now, is there a top-down approach here too? Is there some string theory embedding? So the first thing that I want to say, which relates more to the UV part of these lectures, is that actually when you do these Mellin integrals, we kind of swept it under the rug, but if you do these Mellin integrals, we integrate from 0 to infinity, right? So down here we have the deep IR, up there we have the deep UV. Now it turns out for special amplitudes, in particular in Young-Mills theory, all of these integrals can be nicely done. You might worry that there may be some integrals that just blow up because you integrate from 0 to infinity, and depending on what energy, what powers of omega you have here that come from your scattering event, it may be such that it's actually divergent, right? So let's say if you have, so the deltas we talked about is like 1 plus I times some imaginary number. If you have integrals like this, which is what appears in Young-Mills theory, you can interpret this as a Dirac delta with some 2 pi's. But if this is not a 1, but something else, then this is not just the ordinary Dirac delta. It's some more complicated distribution. Or you might say that, well, actually, this thing blows up because I'm integrating to the UV. This is not what we did in momentum space. In momentum space, we have effective field theory, so all of our ignorance about the UV, for low energy questions, we don't have to worry about what happens in a deep UV, because we can sort of cut off at some energy scale. But if we integrate over all the energy scales, we can't do that. So is there some effective field theory in celestial amplitudes? I integrate all the way to infinity. So do I have to know what happens in the UV? So you might say this is another condition that you can give. A theory is a good theory in the UV if the celestial amplitude is finite. That could be your condition. And maybe this will narrow down the possible UV theories. What happens in string theory to these integrals here that are naively divergent is that in string theory, they're finite. There is no UV divergence. And this is the feature that string theory makes scattering soft. So high energy scattering is very soft in string theory. And this makes these integrals soft when you integrate up to infinity. So could you use this to narrow down and maybe land on string theory is the only theory that has good celestial amplitudes? So that could be your question. You might also ask whether there is a string theory embedding of all of this. So you start with some string theory, and then you sort of land on celestial holography or flat space holography. There is some recent work which goes under the name of twisted holography, which tries to do precisely that. So it goes to some particular sector of string theory where there's some extra symmetry, and you use some defects and branes and so on, and sort of for some special theories, not Einstein gravity, but for some special theories, you can write down an actual string theory embedding of what you might call flat space holography. Okay? And then, of course, here the holy grail would be to find the string theory embedding for Einstein gravity and have a real top-down construction of Einstein gravity. And that would be amazing, because this would then give us a hologram for our world. And by our world, I mean below the cosmological scale, of course. Okay? Good, and now to finish off, let's take a step back. So why do we even think there could be a holographic picture for flat space? Why do we think that? I mean, ADS-CFT is nice, but what if it's just, holography in ADS and that's it? Should we expect there to be a holographic principle for flat space? What do you think? Nobody has an opinion?
Maybe we think it's inherent to gravity.
It's inherent to gravity. Okay, so what's the place that we might go and look if we want to learn something inherent about quantum gravity? What is a good playground for looking at quantum gravity questions? What? Early universe, okay, that's one thing. But I'm a bit more abstract here. By the way, if there is some interesting, okay, let me not spoil this, but okay, what else I could look at? Okay, black holes. Black holes is a good place. Okay, so here's a black hole. What is the special thing about black holes? Okay, it's not really let me, okay. What? Thermodynamics, okay, apparently there's some thermodynamics, something that looks like thermodynamics. What does this tell us? Microstates, okay, let's be less sophisticated. Let's not go there yet, but much more macroscopic. The entropy scale is like the area in units where everything is 1. And we will restore them tomorrow because they will be important. But okay, there's area. So this formula, normally in thermodynamics, how does the entropy scale? Volume. Now it scales as the area. So aren't black holes the place that is like intrinsically asking for holography? Okay, so this is holographic. And this has been the whole motivation behind holography. So there's gravity. When you go to places where quantum mechanics and general relativity kind of clash, you have an object that seems to have a holographic nature. There's a holographic tiling of bits of information, and the entropy is given by that holographic surface. Okay, well, this is I would rather say 2, but let's not take this analogy too far in that direction. Let's just say there is some motivation for holography as soon as you have gravity that says there's something holographic going on. And so this is one of the motivations. So if you are near a Schwarzschild black hole, so if this black hole is charged and you go very near it and this has a lot of charge, so I don't know how much you know about black holes, we'll talk about this tomorrow, but there are black holes that are called extremal, where the charge has the maximum value given a black hole with mass m. And then if you go near those black holes, you haven't entered the Sitter region, right? So this is a place where ADS-50 is good. But black holes in the universe are not extremal as far as we know, so it's the ADS-50 part of our universe is fairly constrained. If this black hole is a black hole that has no charge, it's just as mass, we go near it, there's no nice ADS-50 region. So there's no nice holography that comes from using ADS-50. Still, we are instructed to think that the entropy is given by the area, and so we still have holography, although there is no ADS-50 region here. So it seems that gravity wants to have holography, and so this is one of the motivations why we think that even in flat space, you go near a Schwarzschild black hole, you have flat space near the horizon, that even in flat space we could have a holographic principle. And then, well, throughout these lectures I went through some, some basic and some intricate statements in order to find some evidence for this holographic picture. Okay, so this was finishing off the infrared part of the gravity lectures, connecting it to questions about the UV. We don't yet know how to treat black holes in celestial holography, so that's why I will not continue in that direction, because I have not much to say there. But what we're gonna do tomorrow is we're gonna take this holographic principle for black holes more seriously, and we're gonna ask if we can understand the entropy of black holes. Now, how many of you have had a course on string theory? Okay, great. How many of you have had a course on ADS-50 where you learn about extremal black holes, BPS black holes, and so on? Okay, good. I will not talk about that, so don't worry. So there has been a lot understood about BPS black holes, supersymmetric black holes. This is sort of, one of the major successes that came out of string theory, looking at supersymmetric black holes and giving an answer for what this formula means in terms of statistical physics, in terms of microstates. That's the fancy word that you just said before. But this success is mostly constrained to the special black holes which don't exist in our universe. There is a lot of machinery that goes into this, but I will not talk about that. Instead, I will talk about something much simpler, but in some sense harder. So it's harder because I want to ask the question of what is this entropy for black holes in our universe? So the Schwarzschild black holes or Kerr black holes that we have in our universe, forgetting about the cosmological constant. They have an entropy that's given by the area. Can we understand what the microstates of those are? We don't have any supersymmetry. There is no charge that makes this near horizon region be under de Sitter. So no ADS50, no supersymmetry. Nevertheless, can we say something about the microstates of black holes? So that's what we're going to do tomorrow. Okay, thank you.